For this last lesson of chapter 12, I got to go through some special cases with you. With IB problems, the norm is to always throw in some problems for any content area. They're just a little different, and they sort of make you apply some formulas that you've learned throughout the chapter, but in just sort of a different context and in a different way. And so I'm going to give you 4 examples right here in this lesson. Of course, this doesn't cover every scenario you could ever run into, but I'm trying to give you some different ideas of ways that I've seen this come up in IB tests in the past, and that are going to help you. So here we go. First example, these terms, so that's the first term, second term, and third term, are in a geometric sequence. So find the value or values of k. So in this case, the key word is geometric. One thing that we know about geometric sequences is there is a common ratio, which means the second term divided by the first term would be the same as the third term divided by the second term. So remember, that's how we always found a common ratio, is that you can take any term and divide it by its previous term to get the common ratio, and it's always consistent for every term in the sequence. And so that's the guide to the setup right here, is I did the second term divided by the first term must equal the third term divided by the second term because of that common ratio that exists throughout the pattern. So that was the setup. From there I cross multiplied, so 5k minus 5 times 5k minus 5 on one side, and then this guy times this guy on the other side. And that's what you're seeing all across this first line is cross multiplying. And so I started going through that FOIL process that gave me the setup that you see here. From here it's just cleanup. So I recognize there is a quadratic equation being played out here that I have to solve. So I want to get everything onto one side to make it equal 0. And so that's what you're seeing right here in the next line, was all the terms being put onto one side, make the whole thing equal 0. And then we're going to solve it using any of our quadratic methods from here. One way to do this would be to recognize that 20 goes into all these terms. So I'm going to divide the entire equation by 20. That gives me this new equation that is a whole lot simpler to work with. And so that's always a nice little trick to do. Of course, you could solve it from here. It's just a little more complicated with bigger numbers. So anyway, once you get to here, I chose to solve it by factoring. So these were my factors, which means my solutions are -2 and +1. And so that's where I got my solutions for k. So that's one scenario that we need to be familiar with. Second one, this is another case where these are popular IB style of questions for this chapter. I'm giving you one scenario. They can always tweak this question a little bit to make it a little different than what I'm giving you right now, but I'm trying to give you a general idea of how this would work. So here we go. There's a ball being dropped from a height of 10 meters, and so that's where this begins, is I'm dropping the ball from a height of 10 meters. On each bounce, the ball bounces to 3/4 of its previous height. So automatically, because of this common ratio, I know it's a geometric pattern, and so it started at a height of 10 on the drop, and then it bounced to 3/4 of that right here on bounce 1, so 3/4 of 10, and then it bounced again, and I get 3/4 of the previous height. It bounces again to 3/4 of the previous height, and that pattern just keeps on going, 3/4 of its previous height. So what is the height of the ball on the 4th bounce? So one thing you got to keep in mind on this one is the wording is always a little weird. Sometimes students have a hard time just interpreting what that means exactly is on the 4th bounce. So what they're trying to show us right here is basically after the 4th bounce. So it bounces and then creates a height immediately after that. So this is the height on the 4th bounce. So here's kind of the interpretation on that again is, so here's the drop. And remember, this is like the first term in the sequence right here. This is the initial term. But it's going to drop, and then it bounces, and they would consider this the height of the first bounce, or the height after the first bounce, or on the first bounce, is the way they might word it. And so then it's going to bounce again, and this would be the height on the second bounce, or after the second bounce. This would be the height on the third bounce, and then here we have the height on the 4th bounce, or after the 4th bounce. And again, I just used the pattern of 3/4 to get to this stage. And so this was done all without formula. I was able to come up with this height right here, which is the answer, without any formula involved, just by playing out the scenario that they described here, gave me the height on the fourth bounce. If you wanted to use the formula that we've been using for this, which remember this is just a geometric formula, so that looks like this one. And so I'm using this scenario right here where it's the first term, the common ratio, n minus 1. And so take a look at how that would play out here. Here's the setup for that. So here's the first term, which was the 10, right? That was the drop, was the 10. My common ratio was 3/4. And then right here I have n minus 1, which is 5 minus 1. And the reason it's 5 and not 4 is because the common mistake is to put 4. But I got to see that yes, it's the fourth bounce, but the fourth bounce was the fifth term in the sequence. So I get the 5 minus 1 right here. Remember, the drop was the first term in the sequence, was 10. This was the second term in the sequence after the first bounce. After the second bounce, I got the third term in the sequence. And if I keep going on down the line, right here is the fifth term in the sequence, and that was created on the fourth bounce. And so I could use the formula and do this scenario right here as well. Right here, the total distance traveled by the ball. So we're not thinking of this as moving left and right. We're thinking of this as just bouncing up and down. And so I always put these kind of side by side so that you can see the layout, but we have to view the ball as the sort of the vertical distance that was traveled, not the horizontal. It's just a ball bouncing straight up and down is what they're trying to describe. So the way we have to view this one, and this is the one that's probably the hardest one in this whole lesson, is when we're talking about the total distance traveled, notice that if I just continue letting this ball bounce and it forever goes 3/4 of this height, then 3/4 of that height, then 3/4 of that, 3/4 of that, technically it would never stop. It would never land on 0. I would forever continue to multiply by 3/4 times 3/4 times 3/4. You would never get to 0. You would forever get closer to 0, but you would never actually stop on 0. So we have to view that. Because of that, we're viewing this as an infinite geometric sum. And so for the infinite geometric sum here, we have to remember this little formula right here. This is one formula that is not in your formula packet that you are to be familiar with. So keep that in mind. But it's a simple formula. It's just the first term divided by 1 minus r. And that's the one we're going to apply to this scenario. Keep in mind that if they talked about a total distance, let's just say after the fourth bounce or after the fifth bounce or however they described it, it would no longer be infinite. If they give you a specific term, then we would just use the geometric sum formula, not the infinite geometric sum formula. But worded this way, total distance, it wasn't given a defining ending to it, so we would consider this one to go on forever. The best approach to this is to recognize, in this case, when we talk about total distance, keep in mind that the ball would bounce up and down for every bounce. So we started with this drop of 10, which only goes down 10, but then for each bounce, it's going to go up and then down, and then up and then down, and so it's doing this twice for every bounce. So when it bounced the first time, it went up 7.5 and down 7.5. On the next one, it went up 45/8 and then down 45/8. And then on the next one, it went up this amount and then down this amount. And so these amounts all occur twice because of the bounce up and down. The only one that doesn't occur twice is this guy, because all we did was we started here and dropped it. And so this occurred once, everything else occurred twice. So the approach to that is to separate out the drop from all the bounces so that we can sort of work with our formula that you see here. So here's the idea, is I'm going to separate out the drop, and then I'm going to take into account the bounce heights that all occurred twice. And so here's the separation on that. So I'm separating out the drop, and then I'm doing 2 times all of the bounce heights, which go on forever, because it didn't give us an ending to this. It didn't say the total distance after the 4th bounce, it just said the total distance. And so we're using the infinite formula that you see here. When you do this, here's the key. Remember, I separated out the drop from the bounces. And so when you look over here at how I played out the formula, here's the drop, and then 2 times my bounces. What you have to see when you do this is if I separate out the drop, that means I'm no longer looking at the drop as my first term of the sequence. I am looking at bounce 1 as my first term of the sequence. And so that's why right here you're seeing 15 over 2 as u of 1, or the first term. So I have 15 over 2 as my first term. My common ratio was 3/4, and the rest is calculator work to get this total distance of 70. All right, moving on down into these last two. These are very similar to each other, but these are also very popular IB style of questions for the arithmetic and geometric sequences and series. They love throwing these into word problems as well when they talk about, maybe investments of money, one occurring at one rate and another investment occurring at another rate, and comparing those two. Those are really popular for these. But anyway, look at the first one. The first case, example 3, is going to deal with 2 sequences, while example 4 is going to deal with 2 series. And so that's the difference between these 2 examples right here. So take a look. In sequence A, you start with 50, and you are adding 10 every time in this arithmetic pattern. Sequence B starts with a smaller amount, but this is a geometric pattern, and because it's geometric, that means it's going to grow at a faster rate than the arithmetic. Which means at some point, even though we're starting with a smaller number, at some point these numbers will become bigger and overtake these numbers. And what they're asking for is, at what term will sequence B have a higher value than sequence A? So that's what we're looking for. The easiest approach to these is we're going to take advantage of our calculator here. So take a look. For sequence A, we're going to use the u of n formula to give ourselves a general outline of what's going on for sequence A. So I have my first term of 50. Here's my n minus 1 and my common difference of 10. If I distribute the 10 and do a little cleanup, I can get the simpler look that you see here. And so 10n plus 40 describes sequence A, so that's what we're going to put into our table right here. Sequence B is arithmetic, so we're going to use the u of n, geometric. So we're going to use the u of n formula for geometric patterns for sequence B. I have my first term of 8, my common ratio of 3 over 2, and we're going to raise that to the n minus 1 power. And so there's the general form for sequence B. And again, what we're going to look at here is at what point do these numbers become bigger than these numbers? Because even though this one starts off bigger, the arithmetic growth rate is linear. I'm just adding 10, adding 10, adding 10. But because a geometric growth rate is exponential, multiplying by 1.5 times 1.5 times 1.5, because it's exponential, at some point these numbers will become bigger than these numbers. And that's what we're looking for. So here's the best approach, so we're going to throw these into our calculator as graphs. So I'm going to do this as y1. I'm going to do this as y2. So if you're following along, try that with me. So let me jump over to my calculator. So I already put those in as y1 and y2. So you can pause my video here if you need to take a minute to plug those in. But anyway, let me go to some normal settings here. Actually, for these settings, the window's not even going to matter because it's not the graph that we're going to look at, it's the table. So whenever you have those in, go ahead and hit graph. So you do have to graph it first, but once it's been graphed, all we're going to look at is the table. So graphically, we can see where this is occurring. Here is my arithmetic pattern, 50, 60, 70, 80, 90. That was sequence A. Here's sequence B. And so you can see where at some point sequence B, because it's geometric, becomes bigger values than sequence A. But we're going to take a look at the table to see where that's happening. So go into your table. So notice right here we had the first term in both sequences. Sequence A was started at 50. Sequence B started at 8. Here are their values at term number 2, term number 3. And take a look. You can start seeing where the red ones, with that exponential growth, the red ones right here at term 8 become bigger than sequence A. So right here at term number 7, sequence B was still a little lower than sequence A, but right here at term 8 is where the ones for sequence B become bigger than sequence A. And so one of the things that you're going to be asked to do to show where you get the answer of 8 is to show a couple numbers on your table. And so that's what we did. I showed a little bit of the table that we just got from the calculator. So I showed the first couple terms for each one. Of course, I showed the general rule for sequence A and for sequence B. But then I just showed where the change occurred. So right here at sequence 7, this guy was still smaller than this guy. But right here at term number 8 is where the sequence B became bigger than sequence A. And so I do know that the answer is 8. But if I asked to show in a table proof of where that's occurring, this would be a sufficient table to show that scenario. Let me go down to one more case. This is identical, but it's with series instead of sequences. So these are now sums of a sequence. And so we're using the S of n formulas for these instead of the U of n formulas. And this is a really common mistake made on our test, is to switch when to use the U of n formulas versus when to use the S of n formula. So be careful on that. It would cost you a lot of points. If you were to use the wrong formula, you would get no credit for this because everything will be wrong for this whole problem. So you got to make sure you're using the right formulas. This is going to play out the exact same way. So I'm going to go through this one a little quicker. Again, the only difference is I'm now using S of n formulas instead of U of n formulas. But take a look. Sequence A we recognize as arithmetic because it's plus 5, plus 5, plus 5. Sequence B is geometric because it's times 3, times 3, times 3. So again, even though sequence B starts out smaller, right? 3 is obviously smaller than 36. Because it's geometric, at some point, this sum will become bigger than this sum. And so that's what we're looking for. Remember, don't focus in on the individual numbers. We're looking at sums, not specific terms. So for the S of n formula for arithmetics, I'm plugging in to the big S of n formula here. So remember, we just leave n as n for this. I plugged in my first term. I plugged in the common difference. And you can leave it like this if you want to. All of this can go into your calculator. I did a little cleanup and went for this look because I just think it's simpler to deal with in my calculator, but you could go with either one. Either is accepted. For sequence B, so I'm now using the S of n formula for geometric series. So I got my first term, I got my common ratio here and here. Of course, we can change this to a 2, and so I just wrote it as 3 over 2. To get this look, I feel this is a little simpler, but you could just leave it just like this if you really wanted to. Anyway, I'm going to do the same thing I did up above. I'm going to put this stuff into a table. I have the sequence A scenario right here, sequence B scenario right here. Those are what are going into my calculator in the graphing area. So take a minute and do that. Alright, if you're watching the video, let me point out one thing before I go to the calculator. Here's another really big mistake made on our test. In geometric sequences, in the U of n formula, the minus 1 is part of the exponent. In the S of n formula, the minus 1 is not part of the exponent. And so oftentimes on a test, students will mess that part up, and of course it will cause your answers to be wrong. So be careful in your calculator to do that part correctly. So again, notice here I kept the minus 1 down low, not as part of the exponent. But here was the series A. This is series B. So I'm going to hit graph. And I don't even care what the graphs look like. All my information is coming from the table. So I'm going to let those graphs play out really quick. And then I'm going to jump over to the table. There we go. And I simply need to find, here are their first terms, second term, third term, fourth term, and fifth term. And here's where you can see sequence, the series B becomes bigger than series A on term 5. So 5 is our answer. When we're going to be asked to show this in a table, you always want to show the first couple terms, like terms 1 and terms 2, but then you also want to show where the change occurs. So because my change is occurring at term 5, I want to show the one right before it, term 4, and then I can see now in term 5, series B becomes bigger than series A. So you always want to show all that within your table. And there you go. So that's our answer, is term 5. Make sure that you do answer it. You do need to show that it's term 5 is the answer. That's what we're looking for.